Another point is that actually this y, when we make this definition, y doesn't even need to be a measurable function. So we can take any function which may not be measurable with respect to anything. It could be just some function, and let's take this away. Let's take the assumption about measurability away. Let's take this away. Let's take everything away. What do we leave? We actually even kill this f away. When we don't have f, then we don't have probability measure either. So what are we left with? We are left with omega. It's not the probability space if it doesn't have a sigma algebra. So that's where we are. We have a set. We have any set omega. We have any function. It could be your worst function analytically, your worst nightmare on fractals or non-measurable things. So it could be really, really bad animal, this y. Regardless, whatever it is, we can always write down this definition that we say that we look, okay, we take all preimages of Borel sets and we take the smallest sigma algebra. So let's recall once more, maybe in a picture. So we have any set omega, it could be very nasty looking set. And then we have the real line over here. And we have some function y here. And then what we are doing, we are picking a Borel set there. Borel sets are anyway, they are rather nice objects. So we take a Borel set here. And then we look at the pre-image y minus 1b here. So, and we take the collection of all these type of sets. So that gives us this y pre-image of the Borel space. And this definition makes sense. It is a sigma algebra, and it contains this collection as a sub-collection. So we are done with the definition. And actually, if it so happens that you need to define a random variable, and you are, okay, maybe you assume that you have a function and you think, okay, what would be my sigma algebra for this function? So actually, in a sense, what you could do, you could always say that, okay, I take this as my sigma algebra. So then with this notation, then omega and f gives you a proper measurable space, and you could work with this. You couldn't work with a lot because you don't have the measure there. So, okay, what's the probability measure? That we didn't answer yet, but anyway, for the game about sigma algebras, this is you can always use this concept, and that's actually a common thing to do in probability theory. If you read theory about statistics, mathematical statistics, mathematical finance, so this is used a lot. This notation. It's really fundamental. That's why we are using time here today. Maybe a related thing is another definition. What if we have many random variables, or what if we have many functions? So assume that we have a collection of functions which are maps from omega to the real line. They are indexed by some gamma. Gamma could be a small or huge set, maybe even uncountably infinite, but we have a collection of random variables. We would like to define what would be the smallest sigma algebra that all of these y gamma, everything becomes measurable. What should we do? And the answer is actually that what we can do is that we say that what we require that for every y gamma to be measurable, we need that this pre-image of the Borel sets by the function y gamma should be contained in this collection that we are looking for. And this should be true for all gamma. Yeah. So especially it means that the union of these collections. So we actually are requiring that the union of these collections should be in this some sigma algebra that we are looking for. Yeah. And that's what we want. That's what we are going to take. So again, we are going to say that this is our collection, calligraphic C. It's an abstract collection of sets in the space omega. It's something, it could be bad, but then we again use the definition that we take the smallest sigma algebra containing this collection. That's what we will do, and that's why I'm going to clean this away and write again something very short. Namely, I'm writing here that we take the sigma algebra generated by this collection all pre-images of the Borel sets with this, and that's actually our definition here. So that's how this is defined, and in words, it's the smallest sigma algebra making all these measurable. Okay. We have a couple of definitions. What else? Maybe now it's a time for a little result about this. Yes, let's do a little result. So maybe should we call it a theorem or proposition or lemma? Maybe it's a bit ambitious to call this a theorem. So let me just write a fact here. It's something that's okay. You can call it a theorem if you like. Let me write the fact, and the fact is that sigma y for one random variable. My claim is that this is actually equal to this collection. And that might look a bit confusing. What on earth is this going to mean? It means that if you look at the definition, it means that this smallest sigma algebra containing this is actually this set. So that is, or it est, we are claiming that this collection is a sigma algebra. So we're claiming, I am claiming, you are not claiming yet anything, but I am claiming to you that this is a sigma algebra on omega itself. So if you want to do a smallest sigma algebra containing this, it is itself, because it is already a sigma algebra. You don't need to add anything there. So we can write for this one random variable, there's nothing to extend. And it looks a bit strange, so then let me try to convince you with the proof. Why is this true? Well, I am actually going to prove that this is true, that this collection of preimages is a sigma algebra. And what does it mean? What do we need to do? We need to check three conditions. So we need to check first that does the full space is the full set contained in this collection. So let's look. Okay, we take the full set omega and we ask, is the omega, is it the pre-image of some Borel set? Yes or no? If we look at the pre-image of the full real line, so this is the collection of points in omega that y is mapping to the real line. But because we assume that y is a function from omega to the real line, so y is mapping every point of omega to the real line, and that's why this is the case. And we know also that the full real line is it the Borel set? Well, of course, because Borel, this is a sigma algebra, so it contains the full set. So because this is true, we conclude that omega is contained in this this collection, and we are happy with the first property. We ask, is this y minus 1b, is it closed under complements? Is it stable under complements? So assume that there's some set. Assume that a set A is in this collection. What does it mean? Then A is a pre-image of some Borel set. And if it's a pre-image of some Borel set, then what about the complement of A? Then after a bit of thinking, we can check that it's the pre-image of the complement of B. And this is again a Borel set, because calligraphic B is a sigma algebra. If we have a set there, then the complement is there as well. And now we know that y minus 1 is the pre-image of a complement of B, which is a Borel set. So that's why a complement is also in this collection of the pre-images. Finally, the unions. So if we take a collection, countable collection of sets in this, which are pre-images of Borel sets, so then each AK is a pre-image of some Borel set BK, and then if you look at the union of AKK from 1 to infinity, it is then after a bit of thinking. So do a bit of thinking here. You can check that this is actually the pre-image of the union of the B case. And because this is again a Borel set, because B is a sigma algebra, so that's why this is this belongs to the collection here, and that's the condition C. So with these three properties, full set is there, it's stable under complements, it's stable under countable unions, we can conclude that yes, this is the claim is true, that this really is a sigma algebra. There's nothing to extend, so that's why the smallest sigma algebra containing all the pre-images of Y is this collection. Is that clear? Very good. Then maybe I could ask you, what about this? So if we go back to here, let's maybe clean this up first. Is it okay if I can clean the proof? Shout immediately if it's not. Now it goes away. So we take the proof away, and what then? The question then is, so what we learned that we can take this away. There's no need to extend because this is already a sigma algebra. In some sense, this pre-image is kind of you inherit the good sigma algebra properties from there. You bring it to the to the left side here. My question is, can we do the same here? Could we put the cross there as well? What do you think? Who thinks yes? Let's make a little. Does somebody want to vote? Who thinks no? Give me red light if you say no. Give me green light if you say yes. I get 2 no's. I get 0 yeses. Thank you. The no's are right. This is not possible. Why not? Well, in this case, each of these, no. Each of these is a sigma algebra. That's good. But the union of sigma algebras is usually not a sigma algebra. So that's why we cannot do it. That's why here we still really need to keep the sigma there.